Hello everyone and welcome back to optimization techniques subject. We have started to discuss about the RSM in these lectures. In previous lectures actually, we have started to discuss about design of experiment. Then we started to discuss about the optimization process. I introduced you how to use that linear model to get close to the optimum region. Then how to develop that response surfaces by second order model, which we use to different design, CCD or central composite design, and also BBD or Bacon design to develop that second order model, which is actually a response surface. Now, in this session, I'm going to tell you more about how we can analyze or the process of analysis for the fitted responses surface. Actually, these response surfaces will be something like what you can see in this figure, in these different figures. In examples later, we will also see more of these surfaces. You can see these surfaces can have different shapes, and not always we can get the maximum or optimum point in the surfaces. However, if we have two factors, if we can draw a three-dimensional or 3D graph, we can in most of cases, we can find the optimum point, minimum or maximum point for that surface. For example, for this surface, the maximum point is here. For this is you have minimum here, maximum here, and minimum here, for example. So when we have a three-dimensional illustration of the surface, we can distinguish the optimum point. Then, or in other words, we can graphically determine the optimum point, which it can be done by a counter plot or 3D plot. I have already introduced to the counter plot or 3D plot. So by using these plots, we can say how is that stationary point, that optimum point or maximum minimum point, we call that a stationary point, and we can understand from these graphs where is that stationary point. For example, here, here we have minimum, here we have minimum actually, and here as well. So by this counter plot or three-dimensional 3D plots, we can find that optimum point. Here is counter plot. We have a minimum point here, maximum point, or actually here we have a minimum point. Here we have maximum point. We can easily distinguish or determine the minimum and maximum point or the stationary point actually by these counter plots. And we have a saddle point in the graph actually. So, but these three dplot or counterplot can be we can draw these plots when we have two factors. If we have more than two factors, we need to use numerical methods instead of that graphical method to find these stationary points or the maximum or minimum points. And sometimes also this numerical method is not enough to find that optimum point. But usually we need to use this numerical method to find that optimum point. So when the levels of factors at which the response is optimal can be determined for unconstrained cases by simple calculus. So we need to do some actually mathematical process. We need to do some mathematical or calculus process to find optimum point. Let me start with the case when we have only one factor, k equal to 1. Then the surface which we have, we have second order, the second order model, which shows the surface for this experiment with one factor will be like this, which is this equation is second order model to predict the response when we have only one factor. It is easy for this equation to find that stationary point. You may remember from the calculus and also maybe from the mathematics that how you can find the stationary point. So if b2 is not zero, the optimum response can be found by by finding derivative for the this equation in terms of x. So and then we need to uh, find the result of this equation. We need to uh, uh, put it equal to 0, then calculate the x of this equation. This x actually x here is the factor. This amount of x is the optimum point for this experiment, which has one factor, and so for this amount of that factor, the response will be the optimum. It can be maximum or minimum. It depends on the uh, uh, type of factor, actually. When k or number of factor is more than one, it is not that much easy like what we have here. We cannot calculate uh, this derivation, and this process is not that much easy to be done, especially manually. However, I can introduce you the equation here in case the number of factors is more than one. The second order equation will be something like this. You have already seen this equation in previous slide as well. We can rewrite this equation like this in matrix form, actually, which in this equation the matrix which we have for the constant in the equation, the for k numbers of factors, and also uh, b is the uh, uh, value, actually eigen value for this equation. And we need to solve this equation. You may recall or remember from mathematics how to solve this, but usually the process to solve this also is not that much easy, and we usually use different computer and different softwares, actually, and we need to do the calculation by software to find the uh, a stationary point from this equation. But the process is more or less same, provided that matrix B is not singular, this matrix not singular. Then the second order model has a stationary point. The stationary point means uh, at that point, first partial derivatives with respect to x1, x2, xk, which are the factors of the experiments, are all of them are equal to 0. Then x uh, o, actually, or x0 here will be this much, which is the optimum point. It is also a matrix, which is the, b here is matrix, so this will be also a matrix, will give us the optimum point for x1, x2 up to xk. K. So by if we solve this equation, according to the matrix, we can find the uh, stationary point or optimum point for our experiment. Depending on the nature of B here, uh, the stationary point can be a minimum, a maximum, or a saddle point of the fitted surface. So here you can see how we can find the optimum point for an experiment with more than one factor. And according to the B and Asian values, if you want to know more about the Asian values and B and the process to solve this equation, you may go back and study more on the simple calculus and also mathematics, how to solve this uh, equation, which has this equation actually, which has this amount of the variables, different variables. We have the um, independent variable and dependent variable. How to solve this and how to find the extremum or stationary point for that second order model with the uh, k number of the variables or independent variables. But generally, if B is positive definite and all eigenvalues are positive, we have a minimum. If B is negative definite, all eigenvalues are negative, we have maximum. And if B is indefinite, eigenvalues are positive and negative, then we have a saddle. All of this process, finding these x's, finding the optimum point for different factors, can be done by MATLAB software or other software which usually we use for calculation, mathematical calculation, like what we have here. This is the process actually, which is also occurring during the optimization process in the software. And according to what I show here, also what I showed here, you have learned that you can see also that this optimization process, when we have more than one factor, is not that much easy to be done manually. So usually we use different softwares to find the optimum point for experiments, especially when the number of factor is more than one. We, however, we have the procedure for those factors. We can again use partial derivative to find the optimum point or a stationary point, but it is also not an easy task, and it needs time, and also the possibility of error in our result will be uh, too high. We have uh, also direct optimization procedure like another mid simplex search procedure or Monte Carlo simulation. Both of them are famous method to find optimize or optimum point, which also can be used here for RSM, because here, as I said, in RSM, what is more important is finding that second order model, which we can find by CCD or BBD model. Then optimization process is only finding a stationary point for that second order model, which we have different method. One method I've introduced you here using that Asian values and partial derivatives in terms of each one of those factor or x's. But the most convenient way is using the software. I will continue this course with I will show you how you can do a optimization process by both of those methods, CCD and BBT method, and find the optimum point for two different examples. Let me just review how is the process uh, or checklist of quality for checking the quality of model which is fitted to the responses. First, you need to generate information throughout the region of interest. Region of interest means the level of factors which you think the optimum point is in that range. Ensure the fitted value be as close as possible to the true values. You need to check R square. So this means you need to check to if the fitted model has higher R square. We will see also this in software. Closer to 1, the higher this R square for the model means your model is uh, uh, good candidate to be optimized, to be used for optimization process actually. And also you need to check lack of fit. Lack of fit of a model, I will also introduce you. The lack of fit will show if your model uh, has has that much generality to predict the actual values with high accuracy. I will discuss about that. And also the design of screening, it allows design of screening order to be built up sequentially. In other words, you can follow the process of optimization process, that linear model, then second order, then get closer to the optimum point. In other words, uh, that factorial design, which is the basic type of design, also can be checked if it is selected accurately. And here is also important, try to have as much as possible lower number of the runs, because each run, as I discussed before, needs one experiment. You need to consume time, uh, and its cost will be higher, and it will increase the cost of your project and so on. So try to have minimum number of runs. Sometimes if you increase the number of runs, for sure your model will be more accurate, because as I told you, we have a line here. If we have more point on this line, we can predict this curvature more specifically, and the model will be more accurate. But you need to also consider that for each one of these points you need to run your whole experiment again. I mean, for example, you have temperature, pressure, you need to again set temperature and pressure and run experiments and measure response. So minimum number of runs also is another target, and you need to check if you already have minimum number of runs or not. And also you need to choose unique design points in excess of the number of coefficient in the model. Do not, sometimes the point level which you choose in your design of experiment be closer to each other. Sometimes it is not that much necessary. You need to check if your data point is really required in the to be included in the model. Sometimes you have outlier, sometimes you have data which is too much closer to each other. For example, temperature in a process maybe 20 as the one level is enough. The next level can be 25, maybe 21 uh, degrees Celsius is not a required level to be included for this factor. So you need to check that as well. And also you need to check the bias uh, of the model. You need to check if the model is uh, more when we just consider a range, a close, uh, very limited range, sometimes your model is not that much global and it cannot be completely used for optimization. And it is because the range you have you have selected for your factor may be uh, not a broad range to cover whole possible place of the optimum point. However, maybe your model has higher R square, which means it can predict the response with high accuracy, but it may be only for a small part of the small range of the factor. So you need to check that as well, which your model has a good generality and it covers the range which you may find the optimum point for that real process actually. And you need to check uh, different type of models. Later I will show you like what I mean of the different variety of models. You will see quadratic model is usually the best possible model you can use, but we have also cubic model and also linear model. But usually the quadratic model is more favorable to be used. Up to here is enough for this session, which I have discussed about checking of the uh, model, and what I told you in this short video lecture, we will see more about that in the software. But what you need to learn from this session is you need to check your model, different models. The R square of the model should be high, close to 1, and also lack of fit of the model shouldn't be significant, and try to keep the number of runs as much as possible low. Thank you very much for watching this video lecture. See you next session.